How many of you guys are familiar with my prior work? Okay, so this is a little bit of a continuation on the theme, if you will. For those of you who aren't familiar with this, I'm an APL programmer, and I've been studying the sort of human factors in computing for a while through compiler design and through implementing a compiler that executes on the GPU. So the compiler itself is hosted on the GPU. And through this, I've come to have some feelings and philosophical thoughts on program design, ideas, this sort of thing. And my talks are available elsewhere to get the philosophical background. I'm not going to spend a lot of specific time today on that. And this talk is not really a talk. So I want everybody to feel free to argue and feel free to push back, especially against this code, so that I can see if I can improve this code a little bit. But I was a scheme programmer. And so naturally, where we're going to begin is with some scheme code. And I'm going to be talking today about what I feel is this sugar in the health sense. So in America, everything has sugar in it. And sugar in a small quantity is great. It's delicious. It helps us identify tasty foods that have nutrients, all sorts of great things. But when we stuff white processed sugar into everything, we end up with a health problem. And the same thing as I'm going to claim has happened to us in programming. And it's such a fundamental thing that we've built empires on top of it, and they end up infecting everything. So we have this problem that we don't even realize is a problem, and it's resulting in code that has to be a lot bigger than it needs to be, programs that run a lot slower than they should be, and that use a lot more memory. Somebody else said, oh, well, this is a case for reducing carbon emissions in the world. I'm not going to make that claim, but the point here is that I want to really push back against this attitude and a particular interpretation on premature optimization is the root of all kinds of evil, right? So brilliant proverb, but we're going to get back to why I think that's a misinterpretation. But we're going to do that through a case study. So before we get into this code here, I want to ask everybody what you think, and now if I've talked to you before and given you the answer, don't spoil it for everyone else, but what do you think is the core fundamental building block from a data structure point of view for functional programming, for object-oriented programming, for imperative programming, for almost all programming the way most people do it? Fundamental building block. Sorry? Functions and data. Okay, now if we focus in on the data side, what is the core thing that we think about when we're building data? What is the fundamental thing we all rely on?
Is it a word?
Is it an array? Well, if you push far enough down, I guess you could argue that the operating system is just allocating vectors and you're playing with them. So in some sense, yes. But let's lift it up a little bit above the operating system into our programming languages that we work with. So what are our programming languages built on? Yes. Variables is getting closer to the idea. ASTs are too high level. What are ASTs built on? What do you need to build ASTs? In a traditional programming language. Pointers, references, yes. The pointer is the fundamental innovation that has allowed all of our programming to be the way it is today, right? There's not a structure today that we commonly use in broad-scale general-purpose programming in the way we teach it that isn't in some way related to a pointer. Occasionally, there are some exceptions, but almost everything is a pointer these days. It started with C. Knuth was a big fan of them, right? Almost all functional programming languages rely on pointers as the representation. We have GC, and GC was invented as a way to handle massive amounts of pointers, right? So we made it really, really fast to allocate new data structures in linked styles, and we made it really, really easy to clean them up so that we can collect that memory at the end. We have GC and all of this all surrounded around the pointer. And the pointer is your sugar. The pointer is deeply, deeply inefficient for a huge number of domains, but is the de facto standard for how we do everything. And to use this case study, we're going to go into compilers to look at that. Because the compiler, almost everybody who writes or works with compilers is working with ASTs. And how do you represent an AST? We've got some abstract record system or some record type or something like this that has various node types and data. And oftentimes these are very complex record types because we're dealing with complex languages. And they all have pointers going round and around through the system, right? And they point and they create these graphs or trees, and that's the data structure we use, and we manipulate those. And we transform them into other graphs and trees. And we keep doing this until we get to our target language. So we have some AST coming in from a parser, right? And then we have some number of intermediate languages, and we transform. We have functions that transform each of those structures, those trees, into other trees in another intermediate language. Or an intermediate data structure. And then we go to another IR and another intermediate representation until we reach the bottom layer, which is a flat, usually a flat linearized style of tree that can be turned into assembly language or C code or FPGA plans or any mapping to whatever our target language is going to be. And you would think, oh, compilers are kind of a special case. But think how many domains you work in that are doing that exact same process. Taking in some data structures, manipulating the structure, and then spitting stuff back out. Business data does this all the time. How much of your code is actually doing lots of numerical calculations? How much of it is manipulating the structures of ASTs for some abstract tree form? A lot of it. So this is everywhere, and compilers form a nice little study space. So what I've done here is I've implemented a compiler in Racket using my all-time favorite scheme compiler construction framework. Read Andy Keep's dissertation about this, on how he used this to redesign Shea Scheme's system. But in essence, we have a set of compiler passes here, and we just run those compiler passes using a fold down the structure, right? So we're gonna, we take our AST in, we do some bookkeeping, we start recording some things, we do function lifting, wrapping expressions, lifting guards, counting some children, some lifting expressions, so it's flattening all the expressions out so that they're not in this nested structure. And then we sort of compute the variable references, because this is a lexically scoped language. So we have to compute what's the frame size for a function, how many variables does it have, where are those slots going to go in our memory space, in our stack. And then we have to anchor specific or variable references to specific slots in memory, right? So it's a fairly basic front end, but it encompasses most of what you need for an untyped, lexically scoped language that's sort of functionally oriented. And the big cool thing about NanoPaths is that it provides a way of defining AST languages, right? Sort of in the same way you would define these in a type, like an ADT or something like this, right? So our AST has roots, which is a set of modules, and each module contains a top-level function container, and then that top-level function container contains statements, and those statements are either expressions or functions, and the functions can appear, and there are different types of functions, and there are different types of things. And this is an APL compiler, so it's compiling the APL language with the defun syntax. And so this is all nice. It's easy to read, and it will generate all the necessary record types for us, right? And build the whole AST that we need. It's nice. And it even allows us to do built-in parsing off of S expressions. So that's nice. And what we do is we define a bunch of these languages, and we can diff between the languages, right? These are all, and now think about it, these are all nice features for building languages. And I'm going to come back, and these are all perhaps mistakes in our design of our programming languages. But they're really attractive, right? They're very sugary. So for instance, I can add new terminals in here with diffing. I can do all sorts of stuff. So I can start doing pattern matching on the different nodes. And what's nice about these is I only have to put the nodes I care about in. It will walk the tree all by itself automatically and do all this for me. And I only have to say, for this specific thing, I'm not just going to let it pass through. I want to do something special. But otherwise, it'll do all of the work for me. So it's really nice and convenient because I can just handle only the nodes I care about. Now this one, I'm doing some special stuff with the name, so it's a bit of a bookkeeping thing that's just, blah, blah, blah. And then here's another language. So then we can move from language to language. So the first real compiler pass is uniquely identifying, right? So in this pass, we're taking from language 0, And you can read this, it's a little type signature up here, from language 0 to language 1. And what I'm essentially doing through here is I'm adding a new field to every record, which is a unique identifier for that node, so that I can reference that node uniquely throughout the whole tree. All right, so every node gets a unique reference. And so I use gensim for that and go through. And gensim is fast because we are actually leveraging the pointer concept here in gensim. So fast gensim actually is using the pointer concept a little bit to do some work. And so this, I have to do a lot of work here because I have to annotate every single node in the tree. But notice that I don't have to do any recursive calls, because all the recursive calls are handled syntactically, right, in these little square brackets here with the commas. So it'll recur down on the fields and do the depth first recursion for me. And this is all real nice, and then this goes on, right? Each of these passes is implemented in this way. And this is a very functional style of designing your compilers, because it's a data flow from one end to the other, and every time you just manipulate the tree and you get a new tree. And you manipulate the tree, you get a new tree. It's also typed. So you get some degree of static and runtime type checking on the system to verify that you're producing the right results. And it drives that by the type that it uses in the type system, the defined language form, right? So how many of you guys think, oh, this is a fairly nice system? Or how many of you guys would not be afraid to use a system like this? This is a fairly standard approach to compiler design, right? Use pattern matching. You have built-in recursion handling it for you. You don't have to write unnecessary boilerplate. It's typed. It gives you some type stuff, even in Scheme, which is kind of cool. This is the way everybody does their stuff, right? But, yes, Colin has seen a lot of my stuff before, so he knows there's always a but coming next. But if I can be totally dogmatic or hyperbolic, it's all wrong. It's all wrong. And why? So what, does anybody know why I'm going to, can anybody guess why, what's the danger here? Pointers. Pointers everywhere. Pointers everywhere. Everything here is a pointer, right? Even the names can be thought of as, pointers on some level. So let's start. We'll do this. Let's run this in Racket. And now we can all go get a coffee, because we're already encountering our first performance problem. This is just loading this into the Racket system, into the memory environment. This is just getting this code to get in to the system. And let's pull up the task manager as this runs. What's our memory consumption right now?
Lots. And going up.
And going up. Now, granted, this is because it's doing some orchestration for debugging. But we want that debugging. We want to have some information when our program goes awry so we can work with it. But at what cost? And now notice, I haven't even begun to run this compiler yet. Notice that Racket starts with 128 megabytes of debugging memory limit. If you look in the upper right-hand corner, you can see what I had to bump it up to for it to run this 1,000-line, which 1,000 lines is not a big compiler. But it's a non-trivial piece of code, but it's a 1,000-line system in a nice compiler DSL. And, oh, yeah, it's finished. Woohoo! All right. Pretty good. So just to load this system in, we at least got up to maybe 2.83. And we can do some garbage collection on this. But we're beginning to see the first problem, right? This wasn't particularly complex. So what are we going to do about this? I mean, people will say, OK, yeah, sure. But what have we always been told, right? That's a fact of life, right? In order to do this stuff, sometimes we have to accept a little bit of additional inefficiency for programmability, usability, to make this stuff work. in order to get this code as short and small and concise and as easy to read as it is, we had to do some stuff for it, right? Well, maybe. That has been the traditional wisdom. The traditional wisdom has also been that GC is also good and all this other stuff. So let's look at another version of this compiler. Exact same passes, doing the exact same transformations on the exact same AST. Different encoding of the AST, but let's see what happens if we implement this in a different language. There's the compiler. Maybe I can bump up the font a little bit here. Yeah, it's a little cut off on the one side, so we'll accept that, but there you go. So it's 17 lines by 70. So this is our, we get out to 70 right about there, including our white space. But that's a 17-line version of this 1,000-line program, 1,012 lines, but yeah, roughly speaking. And I can assure you it doesn't use 2.8 gigabytes of working memory to load itself in to the system. If I were to say, do I want to do that? Let's just look at the memory that this one uses. Where is dialog? Yeah, so this uses 1.5, which seems kind of big, and it is, and that's because I have an unnecessary number of variables that are using gigabytes of space for my data. So let's instead, do I want to delete that? No, let me see if I've got this prepped here for this source code.
Are you saying that that's a state situation just because of the way it's in the demo, or is that normal for you?
Well, let's start with a fresh one. And so reset, no, clear. And then let's load in tt.dialog. Let's see if that'll work. Yeah, there we go. Loaded it in. Let's look at the memory of that one. So that's 200 megabytes to load in, including Chrome. And including a whole lot of other stuff, including a Windows GUI, including the whole big shebang to load in that bit of code. And you'll notice it didn't take a long time. But let's that's maybe not a big concern. Let's try actually getting into a less. So this system is the racket system without all that extra overhead. So we'll load in. It'll run a little bit faster. All right. So let's define an AST of 1,000 nodes. Okay. And let's time the compiler on that AST. So pretty good, right? Seems pretty fast. Not so bad.
What's the units?
Milliseconds. So, okay, not too bad. We can bump this up, and that's double the size. So actually, let's just do something like this. Right? It runs a little bit faster. Now, I continued on with this process, and I ran this against the compiler that I have on the other side, right? And let's run it at a slightly larger set and see what the working memory is, because that's what we're going to start with here, right? So let's run this time compiler with gen AST 16384, right? And now we have our, where's our racket? There's our racket right down there. So let's run this guy. Let's watch what happens. Is this what you want to see happen in your compiler? And we can continue to talk about things because this will take a few minutes to finish. What? So what's going on here? Does anybody know why the performance is this way?
It's trolling through the list of references and taking forever to do that. Anything else?
But that's CPU. Why is memory increasing?
Because one tree depends on another.
Is it heat fragmentation?
You're all kind of right. But the fact that you all didn't immediately know why is also a problem.
Well, we've chosen to live with it.
Well, you've chosen to live with it, and you have no idea what the performance model actually is. So given this, while we let this thing run, let's go back over to the Racket version. Right? Let's go up to this first AST. And what's a good, what's a nice short? Okay, let's take this one. Let's say that E4 or E2 is a fairly typical record, right? Because there's a lot of expression nodes that have 2 arguments. So that's pretty typical. How much memory is it going to take to store that? Does anybody know? Does anybody know how to figure this out? We're on a 64-bit machine, so. Well, what's happening here? Do we even know what data types it's using under the hood? We don't. I do, but that's because I know how NanoPass works. Do you want to know how this large, massive system works in order to figure out the memory usage of your program? Maybe, maybe not. That's abstraction at work. But here's an easy way to think of it. This is just a record type declaration. So given that you know it's just a record type declaration, how much memory is it going to use per node? Yeah, just shout it out if you know it.
Yeah, 3 registers, 2 for one for each of the pointers to the arguments, and then 1 to, something about that in itself.
You said how much per what?
3 registers, so if you're on a 64-bit machine, 24 bytes.
24 bytes.
That's a guess.
Okay. Okay. Well, no. It's worse. Because you can't possibly store this amount of information in your pointer reference structure in that size, right? Because you have to have a pointer referring to your symbol. That's going to take up at least 1 pointer's worth. That's 64 bits. You're going to have a pointer to this structure in here, because it's going to have potential nested structures inside. You're going to have a pointer to this one, pointer here, pointer here, pointer here, pointer here, pointer here. That's 1, 2, 3, 4, 5, 6, 7, 8 pointers. So 8 pointers, and how many bytes per pointer do we work with? 8 on a 64-bit machine. So that's what? 64 bytes per node, right? So we can do a little math with that. Let's work off the clear workspace. So we've got 64 nodes, and we know that we have that number of nodes in our AST, right? Star's exponent, yes. So 2 to the 14th. So 64 times 10 to the 19th times 2 to the 14th divided by 2 to the 20th, so that's megabytes. How much space is an AST going to take for that?
What was the divided by 2 times 28?
That's to get us our number in megabytes. The 2 to the 20 gives us our megabyte factor. Sorry? So our node, my AST, I know that my AST starts with 1,019 nodes in it, and I'm doubling that out to 2 to the 14, multiplying that by 2 to the 14. So that's the number of nodes. That's why I put the 16384 that you saw. That's 2 to the 14 gives me the replication of that node. So I'm representing a large tree full of functions that are of typical size and representation. Ooh, I like the cynicism. But you're in the right ballpark, about a gigabyte, right? So if you actually do your algebra, you just do the exponent reductions and you get a megabyte, right? Or sorry, not a megabyte, a gigabyte. So 1 gigabyte of space for that AST. So let's look at the way we did this in APL. We have the AST here, and it has, whoops, there we go. So it has the 16.6 million, nodes in it, which was our 2 to the 14 times 10 to the 19. That's the node size in that. And it also contains a symbol table. It contains exports. It contains a lot of stuff, a lot of data about the AST. So how much space is going to be consumed by that AST when we use our representation in APL? So 63 megabytes.
Why? Someone's getting cute. Where's the magic?
So why? Well, let's think about the representation. So the representation of the data AST coming in from the parser is that we represent it with 4 vectors: a depth vector, the type, the kind, and an n field. So the n field is that name field that you saw in the AST description. The type and the kind is the record type descriptor. And the depth is the node's depth ordered by depth first pre-order traversal. So it codes all of the edge and node information necessary to reconstruct the tree without the additional data about the node contents, right? So now let's think about how much, these are vectors, so these are arrays in APL. How many bits per element in those pieces do we actually need? So the type and the kind, there aren't that many types. There's probably, there's like 10, maybe 12 types of different nodes. And then maybe 3 or 4 different kinds per node type. So you maybe, all of that, the T and the K can both be represented as 8-bit signed integers. The n field, how many symbols do we have in our tree? We don't actually have that many unique symbols in the code. The number of free symbols is fairly small, so that it can also be represented as an 8-bit signed integer, because we're handling symbols ourselves. Remember, every symbol in your normal language is going to consume potentially 64 bits of information. Because we manage the symbol table ourselves, it only takes 8 bits per symbol to represent. And the depth, well, the depth of ASTs is actually relatively small, right? You don't get large depths in the AST. The depth of these ASTs tend to be about, 15, 20 at max. So the max value of D, if we just do the ceiling of D, it's 14. How many bits do we need to represent that? Well, let's be generous and say 8 bits, right? So now, per node, how many bits do we need? We need, per node, only 4 bits, or sorry, 4 bytes. 4 bytes. So you can see where our savings come from, right? But it also comes from the fact that we don't have a bunch of extra pointer information laying around, so that's all implicit. So it's also sort of a compression. We don't have to actually worry about that. And so our AST is orders of magnitude, 16 times, roughly speaking, smaller than the way you would traditionally be told to represent it, right? So remember that I said most people aren't doing a lot of computation on their code. Well, what does that mean your code is doing? Memory manipulation, right? So most programs tend to be very much more I/O bound or memory bound than computational bound. And so immediately we begin to see some potential performance gains here. But it gets worse. Because what are our access patterns in a GC collected language where we don't control the layout and the contiguity of our data? Do you know what your access patterns are going to be for your data? Can you predict that from your language? Do you have any performance model at all on that? You do have one. It's called random. And what is the slowest memory access pattern for modern architectures? CPU or GPU? Random. And worse yet, you have GC, which means GC is going to be blowing all of your caches the moment your tree gets big enough to exceed cache size. And because of the inefficiency of your memory representation, you're blowing cache real fast. And you're functional programmers, which means you're replicating data all the time. Also, meaning blowing your cache and doing a lot of copying. But what have you always been told? Copying data is good because it helps you achieve immutability better. It helps get better guarantees, right? So in your languages, do you have a way, for instance, to insert a new record field into an existing AST in an immutable fashion? Well, no. What do you have to do if you need to add a new field for additional information in each node as you walk through the tree in your AST? You have to copy the whole tree.
Usually the compiler will use consistent data structures on that node.
Will it?
Yes.
Okay.
For recursive data structures.
Okay, so I'm actually very curious about what the state of the art is on this. So if I have an ADT of a given structure and I change that ADT to add an extra field or record node type to every single other ADT. So let me go back to this concrete example. So here I have one field, which is name, that I store. And then down in the other languages, I have to add UID to every node type. Can your compiler basically only add that field and leave the rest of the data completely the same? Almost certainly no, because that would be violating the very principles upon which your languages are built, at least morally. I mean, if somebody added that feature in Haskell, can you imagine the uproar? They wouldn't just be uproar. Even if Simon Peyton Jones decided to throw that in, he'd be dead in a week. Right? I mean, you guys are nice, but not that nice. So what happens here? In a lot of these cases, when you're designing compilers according to best practices in these other languages, you're going to have to traverse the tree a lot. Now, that's actually not so bad from an asymptotic complexity point of view, because most of your compiler passes are, in fact, traversing the tree all the time. They have to. That's just a part of life. But what really gets you is because you're using the GC pointer-based method, it means you're always accessing it in a random pattern that you can't predict, and you're also always reading more memory than you actually need to, because there's no ability to actually optimize your access patterns, especially not at a high level.
It also pushes the problem downstream.
It pushes the problem downstream, and it creates an architectural investment. That means if this becomes a problem, which it does, how many people have complained about slow compilers? It always results in a problem for once you get successful, and you want to be successful. You have a huge scaling nightmare because the only way to fix this is to completely redesign your whole system. You can't incrementally improve performance anymore because you've invested in a representation that is fundamentally unsound for the performance that you might want. So what this representation here, this DTKN representation, I know how many bits it's going to use. I also know the order in which those are going to appear, and they are all contiguous in memory, guaranteed. But I know all of that without ever having to write any of it. I didn't have to write some C-like type saying, I want this thing to be this number of bits, I want this thing. APL handles that all for me, but I can reason about it, and I know what is going to happen. And that contiguous memory means that not only do I get sequential access patterns or consistent strided access patterns, but now I can reorder that tree to map to specific access patterns that I might need for any given pass, or I can use the vector machines, the vector lanes on my CPU. And you need to be using the vectorization on your CPU to be maxing out its performance, especially if you want to do it in an information-dense way. If you're chasing pointers all over the place, you are not maximizing the ability of your CPU to do things. But working with these types of structures, we're able to get really good access patterns and really efficient access patterns, and access patterns that are in some way hardware independent for vector machines. So this code that I showed you runs on the dialog interpreter, no problem. It also runs on the GPU, no problem. Same source code, same algorithm, same structure. So to leverage the GPU, now I didn't have to redesign my entire compiler because it was incompatible with the architecture of the GPU, incompatible with the vector machine. And so now I get access to a whole host of additional performance results. And because I'm using less memory, I can put it on GPUs that have smaller memory sizes than what we normally have. So let's go back to our little guy here. So this is the runtime in milliseconds for each of those passes. Does that feel good to you? And the reason is because you have a compounding set of a compounding set of design decisions that resulted in cascading performance degradation. So, what does that same compiler running on the same architecture, the same CPU and everything, on an interpreter? Racket is a JIT compiled language, so we're going to run it on an interpreter here. Yeah, nothing. Marshall is if you want to know how it works, Marshall writes large significant portions of the interpreter. So he will, guy in the dialogue red maroon-ish shirt, he can verify how dirt simple the language interpretation technology is under the hood on these things. Yeah. It doesn't even, does it store a bytecode yet? No, it reinterprets the source code every time. Yeah. All right. So now let's run that. And we're done. Much faster. On my benchmark machine, on this size, it's about 5-6 seconds. So how does this scale? What does the scaling look like this for when we compare this representation compared to other things? Well, we can start with, what about the source code? What's the complexity factor on the source code? Well, if we look at the NanoPass system, it's about 1,012 lines of code versus 17. The number of tokens in that structure is about 21,000 versus 760. The amount of unique names that are used, the definitions that you have to know, or references you have to be aware of in the structure is 248 versus 74. And the number of nodes in the source code is about 15,000 to 1,000. And that's nice, but if the performance wasn't there, it wouldn't be so great. So let's look at performance. Now, when you read these graphs, remember, they are log scale base 2 on both dimensions. So both of these are 2 to the whatever the number is, size. And these are each multiplied by that factor of 1,019. So this is 1,019, this is 2 times 1,019, and so on down the road. So this is the CPU, on average, across those passes, this is the speed up you get. On the most trivial example, yes?
What are the actual values?
Yeah, so this is the node size, the node count, the number of nodes in the AST that we're working off. And this is the relative speed up versus the Racket system, running on a large desktop machine, not my piddly little laptop, but that's 2 to the 3 times performance improvement.
So 1 over 2 to the 3 in terms of time spent.
Yeah. And so 2 to the 3, what is that? It's basically a 10x improvement for essentially 0 data. 1,000 nodes in an AST is trivial. That's a one-liner in some places, right? And then it keeps going up until we get to about our large data size set, which we saw, which is about a 33x performance improvement. What does this look like when we take that same code, hand compiled to the GPU, and run it? Remember, the same algorithms, same structure, same stuff. We didn't actually have to change anything. We just targeted the GPU with this stuff. So we're about half slower when we have no data. But once we get to a little bit of data, we win. By a fairly...
Where's a typical program going to be?
So
I guess this is compiling APL, right?
this is compiling APL, but the node counts are actually relatively small. But you saw that 1,000-line program had had 15,000 nodes in it. Yeah, that's the tokens. But that 1,000-line program was in the 15,000, 16,000 token range. So I don't know. I'm really bad at log math. Let's see. 2 log 16,000. So that's, no, that can't be right. Is that right? Yeah. So this is what I need to do. There we go. So that's 15, so 2 log of that. That's better. Yeah, so that's in the 2 to the 3 for the 1,000-line program. So that, for that graph, for the 1,000-line program, we're here, relatively speaking. Yes?
The compiler showed us in APL is over 0, right?
The sorry?
How many nodes are in the compiler you showed us for this?
So that 17-line compiler? The 17-line compiler has 1,000 nodes, so it's the 0 here. Yeah. But the full, including the parser and the code generator and the other stuff, that brings that up, right? But so for, basically, we're seeing speedups on the GPU for 1,000 lines of code in Scheme. Yes?
Out of curiosity, do you know where the slowdown comes from for the lower data?
Here? Yeah, it's entirely kernel orchestration, boot up, constant factor overhead. It's basically, it scales really well until you get up to where you're saturating the memory bandwidth on the GPU. But we can also look into each compiler pass, right? So CPU, GPU, that's function lifting. You know, wrapping expressions. Sometimes dialogue does clever things. Yes, okay, thanks. GPU, CPU, GPU. Notice here, this was rather tragic. The CPU isn't beating the GPU anywhere. Now, the reason is this is not because suddenly our algorithms are better. I mean, they are kind of, because they're data parallel. But there are fundamental architectural obesity problems in that other system that are very, very hard, as far as I can tell, to eliminate, right? Because they're part of the design system of the language. They're deep into the way we operate on those codes.
Well, it leads to like asinine stuff, like trying to figure out how to clear your build cache efficiently.
Yeah.
You don't spend a lot of time doing it.
Now, there is one which, yeah, is it this one? Yeah. So here, we're winning all the way up to 2 to the 4 on the traditional one. And the GPU doesn't win until like 2 to the 5. Can you guys guess what compiler pass that is? No. It's literally walking the tree to find the names that we have exported out of the module system. It's the simplest pass in the entire compiler, and it is represented by this line of code. So it says, find all the binding nodes that are top level and remember them. Remember their names. That's the entire compiler pass, is just walking through the AST to find those things. And I even optimized this. I had to optimize this and do something a little naughty. So normally, you have a distinct language for every tree transformation so that you can get type checking. I didn't do that because the performance was too bad. So instead, I optimized it by creating a single language that gets reused a bunch of times, and I just sort of use empty, dead data in certain spaces. So I lose some error checking, and I lose some correctness guarantees. But in exchange for that, I don't have to recompute certain things. I don't have to recopy data. And that's where you started to see some better performance. And so some opportunities for enhancement on this would be to avoid some of that copying under the hood. But you'd have to start hacking on the NanoPass system to get that. And you might have to start hacking on your systems as well to get that, because a lot of people follow this approach. So let's get back to that premature optimization is the root of all kinds of evil. Yes, true. But the right time to be doing architectural and language level optimization is before you start your project. That's not premature. So you don't want to be arguing in favor of very, very bad approaches to architecture, very, very bad approaches to design that fail to scale or fail to have the potential to scale just because you're trying to avoid doing micro-optimizations lower down. Because once you have 10 or 20,000 lines of that compiler written in nanopaths, and suddenly you have to optimize it and make performance improvements, are you going to tell the rest of your team, we're just going to rewrite it in a data parallel language so we can use the GPU? There's a reason nobody has done that. So anyways, that's my, argument, if you will. But to give you some actual numbers, one of the peak performance on one of these compiler passes on the GPU was 1,500 times improvement over the regular in performance. The memory usage on these systems, this all fits within a 2 GB GPU. So working memory is under 2 GB. But the initial memory is 63 megabytes. The working memory on the dialogue system is about 1.5 to maybe 2. And the working memory on Racket, when you run this, is 8 gigabytes. To actually compile that program requires about 8 gigabytes of working memory. Or it will use up to 8 gigabytes of working memory if I don't restrict it to get that done. So we have an approach which uses more memory, takes orders of magnitude more time, orders of magnitude more memory, and is about 60 times more lines of code.
So what's wrong with it?
What's wrong with what? Yeah, so what's wrong with it? It's a perfectly, we should just continue using this programming model because it's clearly working.
Well, the other side of it is how easy or realistic APL is getting to where we're at today with our tooling. So in our heads, we're all just basically going, I'm trying to implement stuff, what am I going to do? Do I just live with what sucks already? Everybody's already sucking it.
Yeah.
Or, do I want to bite the bullet and try to do something that has so many unknowns and seems like a lot of it and maybe works really great in certain places, but how do I actually bring them to me and my work on a daily basis?
It's a really, really, really good question, and unfortunately APL is a really, really bad language at answering that because all of your standard answers don't apply. So it's an active area of research for me. When it comes to computation, we win. When it comes to code size and simplicity, we win. When it comes to maintainability, we win. When it comes to familiarity, we lose hard. And a familiarity is not to be underestimated because there is a non-trivial cost involved there. There's something to be said for that. But our code is in a very bad state right now. Really, really bad state. So maybe it's worth it to try to begin pushing towards addressing the issue.
Might not have choices either. I mean, like removing towards, I'd say Kubernetes and all this stuff is like going in the wrong direction in a sense, right? If you're thinking about load. So we basically are setting ourselves up for failure the more that we let our world and don't produce something that will actually be reliable and last.
Well, but somebody's got to do some risky stuff. I did some risky stuff. My committee hates me because I did this in some sense, so there was an inherent human cost to pursue this research, but I did it because this was the one area where people thought APL couldn't be very effective. So in compilers or any tree manipulation data, they thought, oh yeah, machine learning, sure, AI, number crunching, finance, sure. But doing tree manipulation, you need good recursion, good type systems, and good pattern matching. And there's none of that. Yeah.
So fundamentally, the distinction is instead of operating with a tree based on pointer structures, you've got to pack a tree into some kind of linear format.
So actually, I do use pointers. Okay. I've just put them in their place. So I have a, so, yeah. Oh, where's my pen? Yeah, okay. Give me just a moment. see if it's in here.
So it's not some crazy experiment. It's been around. Dialogue has been around for 40 years. And we have normal clients that don't do this.
It would be great to see like trivial examples of reading files, counting stuff, doing things that if it's accessible, then that's my world, right? Is reading files, making CLI utility, doing stuff with data. So
Yeah.
Yeah, the CLI stuff for the way, the traditional way to write applications doesn't support command line here. Do it, it's really awkward. But I like anything else. That's
more about that. I don't know. Maybe I'll talk to you later.
Okay. So this is the parent vector structure. So I take the depth vector, which has too much interdependence order requirements, and I convert it to a parent vector. That's what the first compiler pass does. And this parent vector contains pointers. And it's pointers to itself, referring to its parent. But now, I just said pointers are evil. Unmitigated pointers, badly designed, are evil. But if you control your own address space, and you control your access patterns, you know exactly how much space you need, and you can manage that. Yeah, I don't need malloc to tell me where to put my data. But I also don't need to work at the low level. This is all very high level, right? So when I walk this parent tree, it's no more complex and possibly even a little more simpler than doing a recursive traversal. So one of the first compiler passes here is to compute, it's this guy right here, is to find the nearest containing function node. So in other words, what is my lexical scope? And so that basically says, from where you are at now, walk up the tree to find your nearest function enclosing node, and remember that. And that's a reverse walk up the tree to find my lexical scope. And it's fast, and it's very, very high level, but it's working with pointers, and it's just a different way to approach the data. Yeah?
You're saying that, by and large, you mentioned that you sort of control your own admin space. You also earlier in this talk said that APL sort of takes care of it for you. So what level of programmer preemptive contiguous does it take in order to get these sorts of numbers? Do you golf on this a lot, or is it sort of a natural way to express?
So you can argue that I golfed on it, but that's because I didn't know what I was going for. So I spent years trying to figure out what is a better way to design the compiler. However, now that I know how to construct it, it's fairly straightforward. There's not really golfing in that sense here. What it is picking your data structure properly. And in this case, I'm always using arrays, but I'm picking how I want to use my arrays. What are the types? What's the shape? What's the data going to be? And what APL provides for me is it will automatically pick the smallest data size necessary to represent that data. And it's called squeezing. And it will, I think it's called squeezing.
Yeah, well,
Yeah.
squeezing is when we take something that's not.
Yeah. So it'll try to push it into the smallest version of the data at various collection points. And there is a garbage collector in Dialog, but for the type of programming that I do, it's not really necessary. And it only has to manage large, contiguous chunks of memory if you write your code correctly. So it's not chasing pointers all inside the vector. And so about 1/5 of the runtime cost that you saw in the Racket version is garbage collection. So that's like 5-6 seconds. It's as much time doing garbage collection as running the whole compiler per pass in Racket. Yeah?
Does that squeezing process have anything to do with succinct data structures?
I don't know what you... Okay, good. Yeah, all right, he knows something.
We don't necessarily have to squeeze data a lot. Actually, usually we can just compute, either compute what data we want, data type we want, or optimistically, smaller data type.
So you were also asking about how APL helps with other data structures. Symbol tables are an example. Most languages require you to have built-in symbol table support because it's hard to write a symbol table support in the language. In APL, there's a single symbol that suffices to convert a vector of names, strings, into a symbol table. And then they're done. So in the parser, it's like 3 characters to get a symbol table optimization on top of my AST to convert all my strings into this stuff. It's not expensive. It's not mentally expensive either. And yet what I get for that is data size control, locality, optimization performance, et cetera. Because I'm working off of structures now that are very, very fast.
Do you think, so I mean, it sounds like the takeaway is use APL, but I'm curious if you think if people were to rethink how to structure compilers in languages we're using a lot today, could we get at least some of these benefits?
Yes. I believe pretty strongly that as people get more experience with data parallel programming, they will come to realize how good APL is. Because there's a reason APL is the only successful way of doing this in production. However, that doesn't mean that you have to jump onto APL right away. It's fun if you do it. It's quite the ride. And I would argue it's the quickest long-term way to get these kind of benefits in a productive way. But what you can do is, the fundamental problem here is misunderstanding your structures and making really bad choices with your language. If you can avoid doing that, you can ameliorate some of that issue, right? So a lot of languages will have structures that give you contiguous region management. Maybe you need to leverage those more. But one of the problems with that is you need the language around handling those memory regions. And languages aren't set up to do that right now. They're set up to do recursive descent over structures with pointers in them. So you're giving up a lot to gain that. And it's a very big cultural shift. You can achieve some of the benefits. Like, so one of the benefits would be in NanoPass just deciding not to do excessive copies if we could get away with it. Or finding some way of cheating under the hood and recognizing that 2 nodes are isomorphic across 2 languages so that maybe we didn't have to copy the data. That might help improve it. We might even be able to get like a factor 5 performance improvement just on figuring out how to avoid doing that in the NanoPass framework. But the problem is those decisions are everywhere, and they will continue to creep up on you because there's a culture around using that stuff. So you have to attack that culture, and that's hard. You can do it. You don't have to necessarily do it with APL, but there are reasons I think that APL is easier to do this in other languages. And it has been tried in other languages, and it's a hard, hard walk. But I'm not trying to discourage you from doing that, because I think this needs to be addressed across the board. Yeah. Yes? Yes. Yep. Yep.
And while, like, on one hand, like, any particular person who might be interested, like, self-motivated to learn it, they can overcome that stuff.
Yeah.
But, like, do you think that it is one of those things that we can sort of take the underlying model and then put it in perhaps an ASCII character set and still get a lot of the same benefits, even if, you might lose a little bit at that cutting edge?
Yeah, so I know we're basically way over time, but the answer to that is people have been trying to do that for years, and it never quite pans out. And I have reasons that I would argue that it doesn't pan out. I've done some HCI thought on why this doesn't pan out, and what it comes down to is that to do array programming like this, you need excellent ability to do pattern recognition on your code. And unless you can achieve the concision, you can't get the high-level pattern recognition as efficiently. And so what you end up with is more unmaintainable code and a semantics that nobody's familiar with. So now, people will disagree with me on that, but I do fundamentally think that one of the important values is the ability to tersely express complex ideas in a visual pattern that can be memorized, that sticks in your mind as a symbol.
But in terms of code critique, Aaron probably writes the instance code of like a UA programmer rather than R3. So
this is true, yes. So I should, thank you for pointing that out. This is not typical APL. This is APL where I'm pushing a particular APL style to achieve a result, right? Other people are perfectly happy to put an if statement in their APL, or use recursion, or a case statement somewhere, or something like this. I think that in general, APL helps to breed caution around those statements, but plenty of people will continue to use those approaches, and they don't have to be rejected outright. I reject them outright because I'm particularly pushing how I think about things. And it leads to benefits, but it comes at an alien factor. Yeah, so any other questions? Are we going to get kicked out or? Okay, I think people are hungry. Thank you. Yes? The dialogue programming competition is running right now, and that would be one of the most fun ways to do it, and they've got a list of resources you can play with.